Hello, and welcome to the second lecture of parallel computing. So today we'll be looking at different aspects of the architecture of parallel computers. So remember from the previous lecture that in a parallel computer, we actually have parallelism at multiple different levels. So for example, we can start with a single processor core, and we'll see that even within a single core, we can find parallelism. Now we can also combine multiple cores together so that they form a parallel processor with multiple cores executing simultaneously. We can take multiple processors and combine them into a medium scale shared memory parallel computer, or we can take a large number of these processor cores and combine them into a larger scale distributed memory system. And so today, we'll be looking at parallelism within these various different levels of the parallelism hierarchy. Okay, so let's start with a single processor, and let's see what kind of parallelism we can find even within this single processor. So now, so the reason that you can find parallelism within a single core is that when you execute an instruction, okay, this actually consists of multiple sub-steps. So for example, in order to execute an instruction, you first of all need to fetch the instruction, and then you need to decode the instruction. Okay, so here, for example, on the right, we have a diagram of a sample processor, right? So in order to execute an instruction, we need to first fetch the instruction, right? And then we need to decode it to figure out what the instruction is, right? And then the instruction might require us to load some data, right? So therefore, we need to have a separate unit on this processor to load the data. Once we have the data in the processor, we need to execute it. So for example, we might be doing a floating point operation or an integer operation, right? And then after you execute the instruction, you need to write the result back to memory. Okay, so and all of this parallelism, right? So we have these multiple steps that need to be done. All of this is implicit within just the single instruction itself. Okay, so this is why this type of parallelism, where you take an instruction and break it into multiple pieces, this is called implicit parallelism. And the way we use implicit parallelism to improve performance is through a process called pipelining. Okay, so pipelining is going to take that instruction and break it into all these substeps, and then it's going to execute the substeps in a pipeline. And the way this works is that if you have, let's say, 5 stages in your pipeline, okay, then at every time step, you can be doing up to 5 things at the same time. And so therefore, you can get up to 5 times faster performance. Okay, so let's go through an example of this. Okay, so here on the right, we have a 5-stage pipeline. So the steps of the pipeline are the instruction fetch, the instruction decode, the execute, the memory operation, and the write back. Okay, now time here is going horizontally. So on the first time step, we're going to take the first instruction and then fetch it. Okay, so that's going to use the instruction fetch unit. Now, on the second time step, you need to decode the first instruction. Right? So this is going to use a different unit on the processor, the decode unit. Right, and since we're now using the decode unit, the instruction fetch unit is now free. Right? So therefore, we can use this instruction fetch unit to fetch the second instruction. So therefore, at the second time step, right, we're actually doing 2 things at the same time. We're decoding instruction 1 and then fetching instruction 2. We can continue on the third time step. So by the third time step, we've decoded the first instruction. So now we can execute it. Okay, and since we're executing the first instruction, then now the decode unit is free, and so we can use it to decode the second instruction, which we've already fetched in the previous time step. And then also we can now use the instruction fetch unit, which is now free in the third time step, and we can use that to fetch the third instruction. Okay, so now we're doing 3 things simultaneously in the third time step. Okay, so if you continue this way, then you see that eventually you're going to fill up all of these stages of your pipeline. Right, so since we have a 5-stage pipeline, then after 5 steps, we will have filled up all of the different functional units in our pipeline. And so we will be doing 5 things at the same time. And if we just continue with this process, right, then since you're doing 5 units of work at the same time, you're processing 5 different instructions at the same time, then you can get a 5 times speed up. Okay, so this is for a simple 5-stage pipeline. Modern processors have even more stages in them. Okay, so they break an instruction into even finer substeps. So for example, 10 to 20 stages. Now, there is a complication with pipelining, which is that if your code branches, right, then you need to guess how to fill the pipeline. And if you make a mistake in this guess, right, so if you have a what's called a branch misprediction, then you actually have to flush your entire pipeline. Okay, so if we, for example, if we have a branch misprediction at let's say at this time step, right, then we actually have to flush all of the instructions. We have to flush all of these from the pipeline. And so, and it turns out that most code branches have branches, let's say every 5 instructions. Okay, so every 5 instructions, we need to make one of these guesses. And if we make the incorrect guess, then we have to flush our pipeline and we lose all of our parallelism. And so we want to make sure that we have pretty accurate predictions for how the branches will go. And so that's why when you have pipelining, you want to combine that with accurate branch prediction. Okay, so this is one type of one type of parallelism, which is pipeline parallelism within the processor. Okay, another type of implicit parallelism is superscalar parallelism. Okay, so here what's happening is that now in the pipeline parallelism, for each of these substeps of the instruction, we only have one functional unit for that substep, right? So we have one instruction fetch unit, one instruction decode, and so on. Okay. Now, when you go to superscalar parallelism, we could actually have multiple ones of these functional units. So, for example, you could have like say 2 instruction fetch units, 2 instruction decode units, and so on. Okay. And now, even if you're executing a straight line piece of code, right? So the code itself might not seem to have any parallelism in it, but because you have multiple functional units, multiple copies of each functional unit, then now you can actually execute multiple instructions at the same time. Okay, so to give an example of this, let's look at this piece of code over here. Okay, so what this is actually doing is it's adding up 4 numbers. Okay, so so suppose we have 4 numbers. I'm just going to draw them by circles, right? And they're located at different memory addresses. So for example, 1000 or 1004, 1008, and 1012. Okay, so for example, this value is located at address 1000, 1004, 1008, and 1012. Okay, so now we simply want to add up these 4 numbers. And the way this piece of code is going to do that is that it's going to load this value into the value at address 1000 into the first register. It's going to load this value into the second register. Okay, and then next it's going to add the value from 1004 to the first register. So basically what's happening is this is getting loaded into register 1, this is getting loaded into register 2, right? And then on the third time step, we're going to add these 2 values together, right? And then on the fourth time step, we're going to take the value at 1012, and we're going to add it to the value from 1008, which is in register 2, okay? And then lastly, we're going to add up these two values, the values in register 1 and register 2. And you see that now we've added together all four numbers, right? Because R1 after the third time step, R1 is the sum of the first two numbers, R2 is the sum of the next two numbers, and then after step 5, we have that we've added together all of the four numbers. Okay, and then we can store the result somewhere. Okay, so this is the code that we're trying to execute. And if we have a superscalar processor, we can actually execute this in parallel. And so this execution will combine both superscalar parallelism and pipeline parallelism. Okay, so this is being shown in the in part B of this diagram. Okay, so what's happening is that suppose we have two instruction fetch units. Okay, then we can fetch the instruction load R1 and load R2 simultaneously in the first time step. Okay, in the second time step, we're going to decode these instructions. But now, since our instruction fetch units are free, we can use them to fetch the second instruction, right? The add instructions. Okay. And then, and then the third stage would be to fetch the operands, right, the values of these instructions. And at the third time step for the next two instructions, we can decode the instructions. Okay, so you see that this execution over here, right, it's a combination of this pipeline parallelism, right? It's pipeline parallelism because, for example, at the third time step, we're using both the operand fetch units, and we're using the instruction decode units, and we're using the instruction fetch units, right? So we're making use of all these different types of units within the processor, right? And it's also using superscalar parallelism because at each time step, right, we're making use of both instruction fetch units or both instruction decode units. Okay, so this way we get two types of parallelism and even more speed up. Okay, now when you execute code in a superscalar processor, right, the execution has to respect the data dependencies. Okay, and data dependency just means that if you have one instruction that uses the results from a previous instruction, right, then you have to execute the previous instruction first before you execute the other instruction. Okay, so one example of this would be the second piece of code over here. Okay, now this piece of code actually does the same thing as the first piece of code in the sense that it is also adding together these four values at 1000, 1004, and these different addresses, right? However, it's doing these in a different order. Okay, and because it's doing these instructions in a different order, there are a lot more dependencies in the second code. And because there are more dependencies, there's actually less parallelism. Okay, because if you want to, because whenever you have dependencies, right, then you have to execute all of the earlier instructions before the later instructions. So you cannot execute those pairs of instructions in parallel. Okay, so you get less parallelism the more dependencies you have. Okay, so why do we have dependencies? Well, the reason is that, so in the second piece of code over here, the first thing we do is we load the values into the first register, right? And then you're going to add the data from this address 1004 into the first register, right? But notice that you have to do instruction 1 before you do instruction 2, right? Because here we're trying to add the value at 1004 to the value at 1000. So you have to make sure that you first load the value at 1000 into register 1 before you can do the second instruction. And likewise, you have to do the third instruction after the second instruction, right? You have to add this value at 1004 into R1, right, before you can add the value from 1008. Okay, so here all of the instructions are dependent on each other, right? 1, 2, 3, 4, 5. You have to do them in that order. Now, on the other hand, if you look at the first piece of code, we actually have a lot of independent instructions. So for example, these two instructions, 1 and 2, right? They're independent from each other because it doesn't matter whether we do R1 first or R2 first, right? They don't affect each other. And also these two instructions, 3 and 4, are independent from each other, right? Because instruction 3 is doing this addition over here, and instruction 4 is doing this addition over here, and these two additions are also independent from each other, right? The only dependency is, for example, we have to do 1 after 3, right? Let me indicate that this way, okay? So, I'm sorry, you have to do 3 after 1. Okay, so there is a dependency over here, and likewise, there's a dependency, you have to do 4 after 2. Okay, but again, there's no dependency between 1, 2, or 3, 4. You can do them in either order. And so the first instruction stream has more parallelism than the second one, and because it's got, it's got less dependencies, and so therefore more parallelism. And so therefore we can get better performance on the first instruction stream than on the second instruction stream. Okay, now there's actually yet another way to run this code. So for example, here, right? Again, the third piece of code is doing the same thing, but it's again ordering the instructions in a different order. So here, instead of loading both R1 and R2, right, we first load R1 and then add it. Okay, so there is a dependency from 1 to 2. And likewise, there's a dependency from 3 to 4. However, when you execute the third piece of code, you notice that there is still no dependency, right, between 1 and 3. And so you can execute 1 and 3 in parallel, and you can also execute 2 and 4 in parallel. Okay, so we still have parallelism in the third example. However, the parallelism in the third example is harder to find than the parallelism in the first example, right? The first example, you look at these two instructions, which are consecutive, right? And you can realize that they're independent. Okay, here instead, the independent instructions are not consecutive, right? You have to look ahead. After the first instruction, you have to look ahead to the third instruction to find the independent instruction. Okay, so if we want to be able to execute the third code in parallel, right, we need to have special hardware in the processor to look ahead in the instruction stream, right? And we also need to reorder the instruction stream because we need to execute 1 and 3 together, right? Even though 1 and 3 are written at following each other in the instruction stream, we have to be able to reorder this instruction stream so that they can execute together. Okay, so basically the upshot is that if we use pipelining and superscalar parallelism, we can get much better performance. But in order to make use of this these tools, right, you need to add extra things into your hardware to detect when you can actually use superscalar parallelism or pipeline parallelism. Okay, and then another part about this is that here you see that when you have multiple functional units and multiple copies of those units, you want to make full use of all of those units. You don't want those units to go to waste. Okay, and one way you can think about how much you're making use of those units is through a diagram of this sort. Okay, so here we basically have time going in the y direction. Okay, so we have we're looking at 4 different clock cycles, and suppose you have 2 different adders. Okay, so what this is showing is that in the 5th time unit, right, we're making use of both adders. Okay, so we don't have any waste at this time step. However, in the 6th time unit, right, we're only using one of these adders. So we have a wasted resource over here. And then, in fact, for the 4th and 7th time unit, right, we have no instruction to execute in these adders, right? So maybe at those time steps, we're actually fetching the instructions. Okay, so we also have a wasted time unit over there. And so our goal is to actually have as little waste as possible. And so we actually want to fill up all of these adders as much as possible. And that makes that maximizes our performance. Okay, so I'll talk about one last type of parallelism, which is VLIW parallelism. Right. So here, the first part of this is just summarizing is summarizing what we talked about on the previous slide. So you have a resource dependency when multiple instructions are going to use the same hardware unit. Right. So if we want to do, let's say, 4 different additions, and we only have 2 different adders, right, then we have a resource dependency. And a branch dependency is when you have a code that can take different paths depending on a conditional statement, right? Like if x is larger than 0, you do one thing. If x is less than 0, you do something else. Okay. And then waste is going to occur when you have no instruction to execute in a clock cycle. Okay, so the final type of implicit parallelism is VLIW parallelism. So this stands for very long instruction word. Okay, so this is basically going to find instructions that we can execute in parallel, but it looks for these at compile time. Okay, so superscalar parallelism also executes instructions in parallel. Okay, but it finds these instructions at runtime. And VLIW finds the parallelizable instructions at compile time. Okay, so there's both pros and cons to VLIW. So the pro is that because you're doing this at compile time, right, then your compiler can actually use very sophisticated algorithms to try to find as many parallelizable instructions as possible. Okay. However, the con for VLIW is that because you're doing this at compile time, you don't know what's happening at the runtime, right? And so there might be parallelism available at the runtime that you cannot predict at compile time. Okay, so because we don't know what the how the instructions have branched and what kind of cache misses we have, and so we might be so if you use compile time parallelism, you might actually miss some instructions which could be executed in parallel. Okay, so this is basically the type of parallelism that we have in a single processor. Okay, so next I'm going to talk about memory performance. Okay, so this is also a very important component of overall performance because, of course, you need to get data before you can do computation on it. Okay, so therefore the performance of your processor often depends on how quickly you can actually get data. Now, when you look at memory performance, the 2 key metrics are latency and bandwidth. Okay, so latency is basically the amount of time for a processor to access a piece of data. Okay, and then bandwidth is the amount of data that you can transfer from the memory to the processor in each unit of time. So, so to make this more clear, let's use an analogy. Okay, so suppose you're driving on the highway. Okay, then the latency would basically correspond to how quickly you're driving on the highway. Okay, so the faster you drive on the highway, the faster you get from your starting point to the end point, right? So so this car that you're driving, this corresponds to the data, right? So the faster you drive, the faster you can send data from the source to the destination. Okay. Alternatively, you can say that the latency corresponds to how long the highway is, right? If it's a shorter highway, then of course you can get from the start to the finish faster. Okay, so that's latency, is sort of the speed of this. Okay, and the bandwidth, on the other hand, corresponds to how many lanes does your highway have. Okay, so maybe you're on a highway where you can only drive very slowly. Okay, but if this highway has many lanes, right, then in each unit of time, many cars are actually passing through this highway. Okay, so so now these 2 different ways of measuring memory performance are actually independent from each other. Okay, in the sense that you could have processors which have, let's say, low latency and low bandwidth, right? You could have processors with high latency and high bandwidth, right? How well the memory system performs in terms of latency is independent from how well it performs in terms of bandwidth. So, of course, the ideal situation would be that if you have a memory system which is both low latency, right, and high bandwidth, right, that's the best possible situation. And the worst situation would be high latency and low bandwidth. Now, these two metrics are actually important. Some of them are important in different scenarios. So for example, latency is more important if you need to do lots of transfers of small amounts of data, right? And this is because since you're transferring just a small amount of data, right, you don't really care about the bandwidth, right? Because bandwidth lets you transfer a large amount of data at the same time, but this is not what we're after here. Okay. However, since we're doing frequent transfers, you want to make sure that each of those transfers is very fast. And so here latency matters more. And on the other hand, if you're transferring a large amount of data, right, then the bandwidth matters more, because you don't really care how quickly the first piece of data goes from the start to the destination, right? What you care about is once the data starts arriving, like how much data can you get per unit time? And this is what bandwidth measures. Okay, so now let's talk about the CPU memory gap. Okay, so as I said, processors, your processor can only compute as fast as the memory system supports it, right? But the problem is that nowadays you have processors which run much faster than the memory can actually transfer data. So what this plot shows is that if you look at the performance of the processor versus the memory over time, then processors have gotten much, much faster, right? They've actually gotten thousands of times faster over the past few decades. On the other hand, memory, right, it's also improved in performance, but not nearly as quickly. And so therefore, there's this gap between the processor and the memory, and this gap just keeps growing larger with time. And this can have a major detrimental effect on your performance. Okay, so for example, suppose you have a processor which can do 100 gigaflops of performance, of computational performance. Okay, however, your memory bandwidth is only 20 gigabytes per second. Okay, let's say you have a latency of 100 nanoseconds. Now, because you have 20 gigabytes per second of bandwidth, right? Then each floating point value is going to take you 4 bytes. And so therefore, in each second, you can only transfer 5 billion floating point values. Right? So even though you can do 100 billion floating point operations, you can only transfer 5 billion of these values. And so therefore, you're going to be limited by your memory bandwidth to only 5 gigaflops, right? Only 1/20th of your actual processor performance. Okay, so now what do we do about this, right? We've built this very powerful processor, and yet we're only getting 1/20th of the maximum performance. Well, the way to solve this problem is through this thing called the memory hierarchy. Okay, so in a computer, we have different types of memory. Okay, so we could have, for example, we have a secondary memory, which is your hard disk. Okay, you have the main memory, which is your RAM. And then you have these things called caches, right? You could have a level 2 cache, level 1 cache, and then finally you have registers within the processor itself. Okay. Now there's a trade-off between these different types of memory in terms of how big they are and how fast they are. Okay. So typically the bigger a type of memory, the slower it is. Okay. So for example, if we're talking about the hard disk, right? These numbers are kind of old. So nowadays you might have a hard disk which is several terabytes in size, right? But to get any data off of that hard disk, right, you need something like tens of milliseconds to be able to find the data on the hard disk. Now, once you move to main memory, right, you might have several gigabytes of main memory, but to access any piece of data on the main memory, it usually takes you several hundred nanoseconds. Okay. Now, as you move up or down the hierarchy, right? So eventually we get to registers, and registers are very small. Okay. We only have maybe a few hundred bytes worth of registers. However, they're incredibly fast. Okay. So each register access might only take you a single nanosecond. Okay. So that would be hundreds of times faster than memory access. Okay. We also have things like caches, right? So the caches could be several tens of kilobytes or several megabytes. But these things are also much faster, maybe 100 times faster than memory. Okay, so in order to get around this CPU memory gap that we talked about, okay, we're going to make use of this memory hierarchy. And so we're basically going to try to store as much data, as much useful data as possible into the fastest levels of this hierarchy. Okay, so to do that, the main thing we're going to make use of are these caches that we have. Okay, so the caches they basically sit between the main memory and the processor itself. So the cache, it's a small piece of memory, but it's very fast. And it's built the reason it's fast is because it lies directly on the CPU die itself. So for example, here we have a picture of a processor, right? So we have the processing cores over here, right? And we have cache sitting directly on this processor. Okay, and so because the data doesn't need to travel far to get from the processor to get from these cores to the cache, this is what makes the cache fast. Okay, so the cache has low latency and high bandwidth. Okay, and this helps us overcome our bandwidth limitations. So what we'll do is whenever we access data, right, we first check. So the processor first checks whether that data is in the cache. Okay, if it's in the cache, then it can get that data directly from the cache and have very small latency. Okay, now sometimes the data is not in the cache. So in that case, the processor is going to have to get it from memory. Okay, once it goes to memory, it's going to take several hundred nanoseconds, and so it's going to be like 100 times slower than if the data were in the cache. Okay, now when do caches work well? Well, we know that the cache is small, right? It might be a few dozen kilobytes. At most, it might be a few megabytes. Okay, so we know that we can't store all of the data that we need in the cache, right? And so there are certain situations, if we need a huge amount of memory, right, then the caches might not work so well. Okay, so we want to find situations where the caches are actually going to help us. And this is where locality in your code comes into play. Okay, so there are two types of locality. There's temporal locality and spatial locality. Okay, so temporal locality, so let's look at this diagram over here. Okay, so the diagram is showing basically time on the x-axis, and then on the y-axis, it's showing which memory locations are we accessing. Okay, so for example, if we look at this part of the plot over here, right, we're accessing address something like 80,000, right? And then after that, we're going to access a very nearby memory location. Right, so these this set of accesses over here are accessing data from around the address 80,000. Okay, now temporal locality means that after you make these accesses, then if you look further in time, you're going to access this data again. Okay, right, and then in fact, so for the same set of memory addresses, right, these addresses from about 80,000 to whatever this is, 81,000, let's say, okay, we're accessing these items over and over. Okay, so maybe you're iterating through this array over and over. Okay, the same part of the array over and over. Okay, now since you're only using a small amount of data over here, now this is where caching can help you, because you can store this data in the cache. Okay, so this might be just 1,000 values. So this is going to fit into your cache, right? Because you have several kilobytes of cache, let's say. Okay, and now you can access that data over and over from the cache, and you can do that very quickly, right? None of these accesses, these subsequent accesses, need to go to memory in order to get the data. Okay, so that's temporal locality, is that you have a small set of data that you access over and over, and you can do that from the cache. Another situation where the cache can help you is where you have spatial locality. Okay, so this is where the data that you access are sort of consecutive to each other. Okay, so you can see, for example, here, right, we're making a bunch of data accesses, and the addresses are basically one after another, right? They're consecutive. Okay, and this and when you have a cache, this is also useful because each time you load data into the cache, you're not loading just a single value. Okay, you're actually going to load a cache line consisting of multiple consecutive values. Okay, so for example, the first time you access the cache, maybe you load all of these consecutive values. Okay, so the next time you access, and so after you've loaded all of these values, then you see that all of these accesses, right, they can all read their values from the cache. Okay, it's only when you get to, let's say, this piece of data. Okay, so this is no longer in the cache, and so you have to load it into the cache, right? So let's say that this load happens over here. But again, when you load, you don't just load one value, you load multiple values. Okay, so that means that the following accesses, again, can get their data from the cache. Okay, so whenever you have these two types of locality in your code, right, then the cache can actually help you get much better performance. Okay, so let's actually look at some concrete numbers to see how much caching can help. Okay, so to do this, we need to look at the cache hit rate. Okay, so this is basically the percentage of your data accesses that you actually can get from the cache. So whenever you do a data access, that data is either in the cache or it's not. Right. So the cache hit rate is what percent of the time is the data you're looking for in the cache. Now, this cache hit rate, you can think of this as a function of how large your cache is. Okay, so the bigger your cache, right, then the more likely your data is going to be in the cache. Okay, and the higher your cache hit rate will be. Okay, so you can look at this as a function, and so here I've plotted this as a so I plotted the cache hit rate as a function of the size of your cache. Okay, and you can see that this function is increasing. However, it's increasing in a concave way, okay, meaning that there's this diminishing returns. So, so this is saying that let's say if you double the size of your cache, okay, you are going to improve your cache hit rate, but not by twice as much. Okay, if you double your cache, you might improve your cache hit rate only by, let's say, 50%. Okay, yeah. So it's a concave function of the cache size. Now, yeah, also the processors have several layers of caches, right? The L1, L2, L3, and so on, right? So each layer is going to be, so the smaller layers, right? The ones that have less storage, right? They're going to be faster. So the L1s are faster than the L2s, which are faster than the L3s. And sometimes, so we saw that the situations where caches help you is when you have locality in your code. Okay, so what if your code does not have locality? Well, then you should redesign your algorithm so that it has greater locality. Okay, that can significantly improve your performance. Okay, so let's see how much you can actually improve the performance. So let's do an example here. Suppose you've got a 1 gigahertz processor, right? And suppose it's got 100 nanoseconds of latency to the main memory. And so let's say that each time you want to get a word from memory, right, you need to make one round trip, which is going to take you 100 nanoseconds. Okay. Yeah, and let's say that you do one floating point operation for each memory word that you fetch. Okay. So now, since you have a 100 nanosecond latency, right, then this means that you can only transfer 10 million words per second. Right, because each word takes you 100 nanoseconds. Okay, so that means that, and since you're only doing one math operation per word, right, this means that you're only going to get 10 megaflops. Okay, even though you could potentially be doing a billion flops, you're only doing 10 million flops. Okay, now suppose you add a cache to this processor. Okay, and now suppose the cache has 5 nanoseconds of latency. Okay, and furthermore, suppose you have an 80% cache hit rate. Okay, then on average, the latency you incur per word is that 80% of the time, right, we're going to take 5 nanoseconds to fetch this word because we can get it from cache. And then 20% of the time we miss in the cache, and then we have to go out to memory, and that's going to cost us 100 nanoseconds. Okay, so therefore, on average, each memory access, each word is going to take us 24 nanoseconds to fetch. Okay, so instead of always taking 100 nanoseconds, we're now taking 24 nanoseconds, And so that means that in 1 second, you can actually fetch 42 million words. Okay, so you can get 42 megaflops of performance, right? So that's like 4 times better than if you don't have the cache. In fact, if you have a higher cache hit rate, right? So let's say that you have a 90% cache hit rate. Well, then 90% of the time you're using 5 nanoseconds, and then 10% of the time you're using 100 nanoseconds for the access. So on average, your latency is going to be 14 nanoseconds, and so therefore you can get about 70 megaflops of performance. Okay, so 7 times the performance just by having this cache. Okay, yeah. So so this shows why it's so crucial for processors to have this cache, right? And in fact, if we go back to the previous slide, then you can see that on a processor, you actually devote a large chunk of your processor space, right, of its physical space, to the cache because it's so useful for improving performance. Okay, so now let's talk about. So now we've talked about sort of the performance of a single processor. Now let's look at how to combine multiple processors into a larger computer. Okay, so we're looking at the next level in the parallelism hierarchy. So we're going to look at different processor architectures. So the simplest processor architecture is just a single core processor. Okay, so what is a core? Well, a core is an independent execution unit. Okay, and it can run one or more threads. So the core is basically going to have, it needs to have a memory controller, right? It needs to be able to fetch and decode instructions. It needs to execute the instructions. It needs registers, right? Which is the CPU state over here. This is basically the registers to store the partial executions, right? And the core has some cache to improve performance. Okay, so the most basic architecture is just you have a single core in your processor. Now, we can actually combine these different cores and different caches in different ways to form different types of processors. Okay, so the so here I'll look at 2 different types of processors. The first one is called the multiprocessor. Okay, so here we again have 1 core per processor, but we have 2 processors over here. Okay. And the way the processors communicate with each other, right, because we need them to work together, so they need to do communication, well, they need to go through memory in order to communicate with each other, right, because these 2 processors don't have any direct links to each other. Okay, another way to combine these cores is using a multi-core processor. Okay, so this is different from a multiprocessor because in a multi-core processor, you only have one chip. Okay, but the chip has multiple cores on it. Okay, so each core, each of these things is a core, right? So we have 1 core over here, and we have another core over here. Okay, each of these is like a sort of a complete processing unit. Okay, it's got its own execution unit, its own state, and so on. Okay. However, the 2 cores, the thing that they share is that because they're on the same processor, they can actually share their L2 and L3 caches. Okay, and they can actually communicate. The 2 cores can communicate with each other through this shared cache. Another benefit to the shared cache is that it increases the cache utilization. Okay, so if you have a cache and if 1 core doesn't need all the space on that cache, then the cache is not being fully utilized. Right. Whereas if you add multiple cores onto the same processor, then you can make better use of that cache. However, you have to be careful because if each of these cores actually needs to use a lot of cache space, then when you put them together and you share their cache, you're actually going to cause conflicts between these 2 processors. You're going to cause thrashing. Okay, so sometimes sharing the cache can improve performance, but sometimes it can also hurt performance. Now, you can have threads on these 2 cores that run simultaneously. Okay, and because the because the cores share the cache, then they can communicate very quickly with each other through the cache. And multi-cores are very popular nowadays because they're first of all cheap to manufacture, right? Because you only need to manufacture one chip as opposed to multiple chips. Okay, and there's also a lot less waste on the multi-core because for the multiprocessor, right? If you have if you have a program which doesn't, for example, use up this entire cache, okay, well then you've got all this space sitting on the processor which is unused, right? Whereas in the multi-core case, they share the cache, and so they can make better use of that. Okay, another way that another architecture is the hyperthread architecture. Okay, so first of all, what is a thread? Well, a thread is an independent instruction stream. Okay, so that means that you can execute a thread is basically you take a program and you execute it, and you need to keep track of where you are in the program execution. Okay, so therefore you need something like a program counter to keep track of where you are. And you also need to have, let's say, registers to keep track of the state of the computation. Okay, but as long as you know the state and the program counter, then you know what's happening with that thread. So a hyperthread processor basically is going to run multiple threads on the same processor. Okay, so in order to run multiple threads, you need to keep track of multiple thread states. Okay, so each thread needs to have its own set of registers and its own program counter and stack. And now a program can run multiple threads simultaneously, right? And because these threads are running on the same processor, then they can communicate either through the memory or through the cache, and they can cooperate on a problem. Okay, so the terminology for this is simultaneous multi-threading. Okay, so and the advantage of building this SMT processor is that when you want to run multiple threads, right? Notice that you don't have to duplicate the execution units or the cache. You just have to duplicate these CPU states, right? And the CPU state is very cheap because it just consists of some registers, the counter and the stack, right? So it's very cheap to replicate these. Yeah, and so therefore we're going to call each of these things over here, we're going to call this a logical processor. Okay, and you can actually put several logical processors onto the same core, right? And you don't need to duplicate most of the hardware. You only need to duplicate a subset, a cheap subset of this hardware. And so this is a pretty easy way to get some extra performance on this processor, right? So for example, if in your execution units, let's say that you have a floating point unit, right, that can do floating point operations, and an integer unit. So if you only run one thread, right, then you're only going to make use of one of those units at a time. Whereas if you run multiple threads, then you can use both units, right? So you can potentially double your performance. Now, in practice, you're not going to double your performance because, for example, what if both threads want to make use of the floating point unit, right? Then they're going to conflict with each other. Okay, so in practice, you don't double your performance, but you usually get some sort of extra performance. So different vendors implement this SMT idea in different ways. So for example, Intel has an implementation called hyperthreading. They can basically run 2 threads per core. Okay. On the other hand, Sun can actually run 8 threads on a core. Okay. Now we talked about multi-cores and we talked about hyperthreading, and you can actually combine these. Okay. So you can have a multi-core hyperthreaded processor. Okay, so here in this picture here, we're showing 2 different cores, right? So we know it's a core because it's got an execution unit and a cache, right? And then here it's a second core with its own execution unit and cache. And this is being hyper-threaded because we have different CPU states which are reserved for each thread. Okay, so on this processor, we can actually run 4 threads at the same time. And this architecture is actually widely used in practice. So if you look at most commercial processors, right, like this Intel Xeon processors, the AMD processors, IBM processors, all of these are going to combine both multi-cores and multi-threading on each core. Okay, and in practice, so I said that when you do this hyperthreading or multi-threading, right, you get better performance. So in practice, you might get something like let's say 15 to 30% better performance. Okay, of course, this depends on your application and on how you schedule the threads. Okay, so sometimes when you run several threads concurrently, you could actually have worse performance than if you just run a single thread. Okay, and this happens, for example, when the threads compete for resources, like if they need to compete for the cache. Okay, and if this happens, right, then you can detect this through code profiling, and the processors usually allow you to deactivate the multi-threading when you actually get worse performance. Okay. All right. So this is a sort of a picture which sort of shows all of the different architectures that we talked about. Okay. So for example, here up top, right, we have a board which allows you to have 4 processors. Right. Each of these squares has a processor. On the next diagram, we have, let's say, a hyper-threaded processor. So it's got a single core, but this core can run several threads at the same time. Right. Next, we could have maybe a multi-core processor. Right, so this is a single processor, but there could be, let's say, multiple cores in here. Okay. Yeah. So yeah, and the diagrams below just sort of show again what is actually happening within the processor when you have these different types of processors. Okay. So the final type of architecture I'll talk about are GPUs, and sometimes they're called GPGPUs, meaning general purpose graphics processing units. Okay, so we're going to have a pretty sizable portion of the course devoted to GPUs. So I'll talk about these in much more detail later. But right now, I just want to introduce the basic concepts of GPUs. Okay, so the GPUs are actually massively parallel, in the sense that they actually have thousands of processing cores, right? Unlike these multi-core processors, which only might have a few dozen processor cores, the GPUs have thousands of processing cores. And so, for example, in this diagram below, right, here, every one of these green squares is supposed to represent a core. Okay, and the cores, so even though we have, let's say, thousands of cores, right, we're going to package these cores together. We're going to combine some of these cores into what's called a streaming multiprocessor. So for example, we could combine 32 of these cores into a streaming multiprocessor. Okay, and then a GPU would consist of several dozen SMs, each of which has 32 cores. Okay, so each of these SMs can run, let's say, 32 threads simultaneously, or in fact, it can run more than 32 threads, but only 32 simultaneously. Okay. And all of these cores, ideally, all of them are doing the same instruction, right? If they do different instructions, then as we'll see later, we actually get a performance hit. Okay, so even though we only have a few thousand cores, on GPUs, it's going to turn out that you can run tens of thousands of threads. Okay, so each core is actually running multiple threads, right? And when we get to the GPU portion of the course, I'll talk about why this is needed to get good performance on the GPU. Okay, so we talked about how to classify processors in terms of their cores and how the cores are arranged on the processor. So now, so next I want to talk about this thing called Flyn's taxonomy, which is a different way of classifying processors. Okay, and this classification is based on the instructions that the processors are executing in parallel. Okay, so so this taxonomy basically has 4 different types of processors. Okay, so the first type is called SISD. So this stands for single instruction, single data. Okay, so the single instruction basically means that you have a single processor which is doing one instruction at a time on a single piece of data. And so this is just a conventional sequential processor. So next, you have something called SIMD, single instruction, multiple data. Okay, so here, again, you're doing a single instruction, let's say an add instruction. Okay, but you're doing this on multiple pieces of data at the same time. Okay, so I'll show you an example of this later. So this is a very popular type of architecture, this SIMD. Next, you could have MISD. Okay, so this would be multiple instructions, single data. So this is not a very common architecture that you see, but you could argue that pipelining is somehow a form of MISD, right? Because in pipelining, you do multiple ones of these substeps on the same piece of data. And then lastly, you have MIMD, which is multiple instruction, multiple data. Okay, and that is the most general form of the processor. And then depending on the type of hardware that you're running, you would try to use different types of these processors. Okay, so let me first talk about, so the SISD is not very interesting because it's just a sequential processor. So let me start by talking about the SIMD processors. Okay, so for the SIMD processors, we have multiple pieces of data that we're processing, but you're using the same instruction on all of these, on all of the data. Okay, so the way to draw, so we can draw a diagram for that where we have a global control unit, right? So this is getting an instruction from memory, and then it's sending the same instruction to all of the processing units, right? So each of these processing units is going to execute the same instruction, but on a different piece of data. Okay, and the processing units are executing synchronously, meaning they do the instruction at the same time. Okay, so one example of where SIMD is useful is suppose we're trying to add two arrays. Okay, then if you do this in a sequential fashion, right? So here we have an array A with 4 values, array B with 4 values, and you just want to add them together to get an array C with 4 values. Okay, so if you do this sequentially, then we're just going to add the first value from A and B, right? And then the second value and so on. Right? On the other hand, if you have an SIMD processor, right, then here what we want to do is you want to do the same instruction, right, the add instruction, but you want to do it on multiple pieces of data at the same time. Okay, so you can use an SIMD operation for that. And in fact, when you do that, you can do all 4 of these adds in a single instruction. Okay, so you can do it 4 times faster than the scalar example. So SIMD processors are actually very popular today. Okay, it turns out that there are many programs which make use of this SIMD paradigm. So for example, if you I showed you that when you add together vectors, you're going to use SIMD, right? Well, many other types of linear algebra operations, for example, matrix multiplication. Okay, they can also make use of SIMD, right? And many machine learning algorithms are based on basically matrix multiplication, and so so these SIMD processors are very useful for machine learning, and they're also useful for things like computer graphics or for video. Another nice thing about SIMD processors is that they're very cheap to implement, right? Because you only have the single global control unit here, right? So so this control unit is fairly complicated because it needs to fetch instructions, decode them, to do branch prediction, and many other things. However, you don't because all of the processing units are doing the same instruction. You don't need to duplicate this in your processor. You can just have one of these things. Okay, and so examples of SIMD processors would be things like GPUs. Okay, well they actually use something called SIMT, but it's very similar to SIMD. Okay, you also have these, for example, the AVX instructions in Intel processors, right? And the so those are SIMD operations, and the IBM Cell processor also has SIMD processors, the SPUs. And in fact, if you look at the very early generation supercomputers, they were basically just a very large SIMD processor. So those those computers could actually do the same instruction on thousands of bits at the same time. Okay, so they had very wide lanes. Whereas for modern SIMD, we're not going to operate on thousands of pieces of data at the same time. We might operate on something like 4 to, let's say, 32 pieces of data at the same time. Now, SIMDs do have their drawbacks. So for example, SIMD requires that the processors execute the same instruction. Okay, we perform the same instruction on multiple pieces of data. But what if you want to perform different instructions on different data? Okay, you can still do that on an SIMD processor, but it's less efficient because you need to have basically you need to deactivate some of your processors when you're doing different instructions. Okay, so in this example here, right, what we're doing is we're looking at this. So we have, let's say, 4 processors over here, right? And each of them is looking at a value b, right? And if it's 0, then the processor is going to do one thing, and otherwise it'll do a different instruction. Okay. So in this example over here, so for the 4 processors, the first processor and the 4th processor are going to satisfy the b equals 0 condition. Okay. So on the first time step, both of them get to do this c equals a instruction. Right. However, the other 2 processors, P1 and P2 over here, right? Since their b is not equal to 0, they're not going to do the c equals a instruction, right? So therefore, on the first time step, since we require all processors to do the same instruction, okay, then we just have to deactivate P1 and P2 over here, right? They don't do anything in the first time step, okay? And in the second time step, right, we're going to do this c equals a divided by b operation, which will be done by P1 and P2. Okay, but at that time point, we're going to deactivate the P0 and P3. Okay, so even though we have 4 processors, right, we can't do all of the steps in, we can't do all of the instructions in one step. We need to take 2 steps because we need to deactivate some of the processors. Okay, so this situation where you have different instructions done by different processors, this is called branch or instruction divergence. Okay, and so here we have two-way divergence because we have 2 different branches that we can take. But if you have k different branches that that the processors need to take, then instead of taking 2 time steps, you would need to take k different time steps. Okay, so SIMD processors are not good when you have this instruction divergence. Okay, sometimes when you have code which is heavily data dependent, you will have lots of branching. And in those situations, you may not want to use SIMD processors. Another situation where SIMD doesn't work well is when the different processors are very imbalanced in terms of their load. Okay, so if you have, let's say processor 0 has a lot of things to do, okay, whereas the other processors only have a few things to do, then basically P1, P2, P3 will be idle for a lot of the time, whereas P0 needs to execute for a long time. Okay, and these imbalanced workloads show up in things like graph algorithms or sparse linear algebra algorithms. Okay, so that's SIMD. So next, let's talk about multiple instruction, multiple data. Okay, so this is basically a general purpose multiprocessor system because you can do different instruction on different pieces of data. Okay, so the way to look at that is that you have multiple processors, right? So here we have 4 processors. Each of them has execution units and control units to get their instructions. Okay, so all of these can be doing different instructions simultaneously. Now it turns out that if you look at most processors in use, there's somehow a combination of MIMD and SIMD. Okay, so for example, if you look at the Xeon processor, okay, so each of these processors has multiple cores, right? So each core can do its own instruction. So therefore, these different cores represent multiple instructions on multiple pieces of data. However, within each core, they also implement the SIMD instructions. For example, the AVX instructions. Okay, so altogether, this Xeon processor is a combination of MIMD on the cores and then SIMD on the AVX instructions. Another example is a supercomputer. Okay, so these often contain general purpose processors, for example, Xeon processors, right? So those would be the MIMD component of the supercomputer. But they also have a bunch of these co-processors, for example, GPUs, right? And GPUs are basically SIMD processors. Okay, so the supercomputer also is a mixture of MIMD and SIMD. Okay, so that's all about the processors. So next, let's talk about how the processors are connected to each other, okay, and how the processors communicate with each other. So this is going to be through an interconnection network between the processors, okay. So whenever the processors need to do some sort of cooperation or share their data, right, they need to transmit this data on the interconnection network. Now, there are different ways to build this network. So, for example, it can be built using either links or switches. Okay, so the difference is that the links are a fixed connection between two processors. Okay, so for example, over here, right, we have a bunch of links which are fixed connections between these different processors, the squares. And on the other hand, the switches, right, they allow the data to actually travel in different directions. So here in this in the example on the right, if you have a piece of data that's like flowing into this switch over here, right, then the data can either go to this processor or it can continue on in this direction. So if you build a network from links, right, then the structure of the network is static. Right, because it doesn't allow you to move the data in different directions. Whereas if you build your network based on switches, right, then you can actually route the data between the processors. And when you build these switches, you also need to add other components like buffers, right? And you might want to do some sort of broadcast on these switches or multicast. Okay, so the switches get much more complicated than the links. And in fact, if you want to build a switch which has a certain degree, meaning so the degree is basically how many incoming ports there are and how many outgoing ports there are, then the number of wires you need for that switch is going to be quadratic. It's basically the product of the number of input ports and the number of output ports, right? So for example, if you have a situation where you have, let's say 3 input ports, right, and then 4 output ports, right, then in principle, you need to have wires between all of the inputs and all of the outputs. Okay, so this is going to be the product of the number of inputs and outputs. Okay, so now using these the links and the switches, we can build basically there are 2 large classes of memory architectures for parallel computers. So the first class is the shared memory architecture, okay? And for the shared memory, we have a single memory address space for all the processors, okay? And this basically means that any address can be accessed by any processor, right? Because all of the memory is in a single address space. And the advantage to this is that it makes a program much easier to write about, to write and to reason about, right? Because you don't have to think about, say, multiple copies of a data item, right? There's only a single data item, and it's always in the single memory address space. Now, in practice, when you actually implement one of these shared memory architectures, right, even though logically all of the memory is together in one address space, you can actually implement it physically using multiple memory blocks. Okay, and then so each memory location address would actually be located in different blocks, right? Would be located in one of these blocks, and the operating system would take care of finding which block of data of memory has the data. Now, so the advantage of shared memory is that it's easier to write programs for them, but the disadvantage is that they do not scale to very large sizes. And the reason is that because all of the processors need to access the same logical piece of memory, right, then the processors need to be connected to each other through the communication network. Okay, and it's very hard to build a large communication network which can connect all of these processors. And so in practice, the shared memory architectures are going to be limited to, let's say, a few hundred processors. Now, you can improve the size of these shared memory architectures somewhat by adding caches to the processors, right? But when you do that, you also need to add a cache coherence protocol. Okay, and the cache coherence is going to incur a cost on its own. Okay, so next lecture we'll talk about ways to do cache coherence. And so even when you add caches to these shared memory architectures, you're still limited to, let's say, a few hundred processors on the system. Okay, so for the shared memory architecture, even though all of the processors can access this single memory address space, it doesn't mean that all of the accesses have the same cost. Okay, so there are two types of shared memory architectures. There's the uniform memory access and the non-uniform memory access. Okay, so so the uniform memory access would be in this example, right? We have all of the processors are basically the same distance away from the memory, and so each of them can access the memory using the same amount of time. Okay, and for the non-uniform memory access, right? Then the processors are at different distances away from different pieces of memory. Right? So each of these processors can access any of these pieces of memory. So there's a single address space, but the address is physically located at a different distance. So for example, it's faster for CPU 0 to access memory from this first memory bank than from, let's say, the third memory bank, right? Because it's got a larger distance to travel. Okay, so the next major memory architecture is distributed memory architecture. Okay, so here, instead of all of the processors having a single logical address space, each processor has its own memory space, and it can only directly access its own memory. However, and this is illustrated in this figure over here, where we have, let's say, 4 different processors, right? And each has its own piece of memory over here, right? So now, what if you want the first processors to access memory from the second processor? Well, then this has to be done by going through the interconnection network. And in fact, the first processor needs to send a message to the second processor, right? It needs to first locate where the memory it wants to access is at, right? And then it needs to send a message to that processor. And so for this reason, this is also called a message passing architecture. And so the disadvantage of these distributed or message passing architectures is that now the programmer needs to keep track of where the data is, right? So previously for the shared memory architecture, if you want to access a variable, let's say X, okay, well, it's always going to be located in that single address space. So the programmer doesn't need to think about where X is. But now, if you're in the distributed memory architecture and you want to get X, you first of all have to figure out which processor has X. Okay, so it makes it much harder for the programmer. However, the advantage to distributed memory architecture is that because the processors don't need to share a common piece of memory, then now you can build much larger systems, because these systems, each of these processors is more isolated from the other processors. Right, it only needs to directly access memory from its own processor, and you can connect a large number of these processors through a network. Now, in practice, most computers are a combination. Most large-scale parallel computers are a combination of distributed memory and shared memory. Okay, so for example, if you look at a supercomputer, right, then at a high level, it's going to have a distributed memory system. Right, it has many of these let's say cabinets or nodes, right? So each of these cabinets or nodes has its own memory. But within the cabinet or the node, you might have a shared memory architecture. Okay, so at the high level, it's going to be distributed memory, and at the lower level, it's going to be shared memory. Now, there is another type of memory architecture called a network of workstations. Okay, so these things became popular back in the 90s, and basically all you need to do to build one of these network of workstations is you just get a bunch of workstations and you get some network cards and then you hook them up. Okay, so it's very cheap to build one of these systems. And when you do, when you build this thing, you can get pretty high performance and the cost is very low. Another advantage to this is that so as you get faster processors, you can actually swap out the current processors, the current slower processors, as you get access to faster processors. Okay, and it's also easy to modify these the software on this NOW system. And so examples of these would be things like a Beowulf cluster, or you have these things called SETI at home or folding at home. Okay, so these are huge distributed systems consisting of thousands or even millions of computers, and they're connected just by either very cheap networking equipment or sometimes just through the internet. Okay, so now let's look at some specific architectures for the communication systems. Okay, so the first architecture is the bus architecture. So this is the simplest memory architecture, and here what you have is you have multiple processors, right? And all of them are connected onto this memory bus, the single memory bus. Okay, and in order to do communication, a processor needs to get access to this bus. And once it gets access, then all of the other processors cannot use the bus. Okay, so the processor needs exclusive access. Okay, and so in order to do communication, you need to do some sort of conflict resolution between the processors. Because if all of them want to communicate, then you have to pick an ordering for these processors to do the communication, right? Because only one of them can use the bus at a time. Now, the advantage to the bus is that it's very simple to build the bus, right? Because you just need basically to connect the processors, in a line. Okay, but the bus, the disadvantage is that it's got very limited bandwidth, right? All of the processors are connected on the same communication medium, right? So this medium becomes a bottleneck. You can add some caches to these processors to lessen some of this memory traffic, right? Because once you have the cache, then if the data that a processor needs is sitting in the cache, then it doesn't need to go through the bus anymore, right? It can just go read from the cache. Okay. However, even with these caches, you're not going to be able to build very large bus-based systems, right? You might scale to something like a few dozen processors, but that's it, right? And these buses are usually used for the shared memory type architecture. Okay, so next you can build a crossbar architecture. Okay, so this is built using switches, and this is more of a high-end shared memory architecture. And the way this works is that so here we have a bunch of these crossbars. So each crossbar allows communication either in the horizontal direction, so the data can flow in this direction, or if the switch is set, right, then what's going to happen is the data can actually flow vertically. Okay, so by setting these switches in different ways, we can achieve different communication patterns. And in fact, this crossbar is non-blocking in the sense that it allows all of the processors to communicate with each other simultaneously. Okay, so for example, if we have P processors over here and then let's say B memory banks over here, right? We can actually implement any memory access pattern. So for example, we can have an access pattern like this, right? Okay, so this is where PI is going to access memory bank I. Okay. Alternatively, if you set the switches in a different way, right, you could also implement a memory pattern, access pattern like this, right? Okay, so basically the memory bank that one processor accesses does not prevent other processors from accessing other banks. Okay, so these crossbars can achieve much higher bandwidth than the bus, right? Because we can have all of these simultaneous accesses on the crossbar, as opposed to just the bus, where you only have one access at a time. But of course, it's quite expensive to build one of these systems, especially if there are many processors and many memory banks. Yeah, so these systems are more scalable than the buses, but they're usually still limited to, let's say, a few hundred processors. Now, both the bus and the crossbar are one-stage networks, meaning that the message, the data going between the, let's say, the processor and the memory, right? It just goes through a single stage. It's not routed anywhere. Now, you could actually add, and because it's a single-stage network, then it's limited in its bandwidth and scalability. Now, you can actually improve the performance by adding some routing to the data. And here, you can build a multi-stage or multi-hop network, where the messages are going to go through several other processors in order to get to their destination. Okay, so you can think of these processors as a graph, basically. Okay, so here, for example, you have 6 processors, and in order to send messages between the processors, you might have to traverse several links. Okay. Now, we want to look at the performance of these multi-hop networks, and there are several ways to do this. One is by looking at the diameter of the network. So the diameter is the distance between the farthest pair of processors in the network. Okay, so for example, here the diameter of this network would be 2 because the farthest pair of processors would be, for example, this pair. Okay, this processor and that processor, it needs to go through 2 hops. Okay, so the more hops you need to go through to send the message, then the longer it takes to send that message, right? And so that's going to increase your latency. So therefore, we want multi-hop networks with small diameter. Okay, another way to measure the performance of the network is using the bisection width of the network. Okay, so this is basically saying that suppose we cut this network in half. Okay, so we have a network here with 6 processors. Suppose we put 3 processors on one side and 3 on the other. Okay, then how much communication can there be between these 2 halves, right? So suppose we cut the processors in half like this. Okay, right? So we have these 3 processors are on one side and the others are on the other side. Now, the amount of communication, the maximum amount of communication that these 2 halves can do with each other is basically going to be equal to the sum of the capacities on the edges that are cut. Okay, so here we have a bunch of communication links. Each of them, let's say, has a capacity, which can be different. Okay, so here, by splitting the processors in this way, we're cutting these 3 links, which have a combined capacity of 4. Okay, so the bisection width of a network is basically the minimum capacity that you achieve when you split these processors into 2 halves, into almost equal halves. Okay, so now we want a bisection width to be as large as possible, right? Because if we have a small bisection width, then that means that processors on one side can't really communicate with processors on the other side, because there's not much bandwidth between these 2 sides. Okay, so we want to maximize the bisection width. Yeah, so so again, we want to, for diameter, you want this to be as small as possible, and for bisection width, you want this to be large. Okay, another way that you can look at this these networks is in terms of their cost to build the network. Okay, so for example, if you have a processor with, a network with many links in it, right, then it costs you more to build that network. Okay, so one way to measure cost is just how many links are in the network. Okay, so now let's look at several different types of network topologies, and let's compare these topologies in terms of these metrics like diameter or bisection width. So the first topology is just a linear array. Okay, so suppose that you have p processors, right, and each processor is connected to its neighbors in this line. Okay, then the diameter of this topology is just going to be p minus 1, right, because it takes you p minus 1 hops to get from the first processor to the pth processor. Okay, the bisection width is now if you split this network in half, right, how much communication bandwidth you have between the 2 halves. Well, if you chop this network in half like this, right, then there's only one communication link between these two halves. And so the bisection width is very small. It's only 1. And the cost of this network is p minus 1, because we need p minus 1 links in this network. So this linear array, this 1D topology, is not very good because it's got a very high diameter, right? If you have a large number of processors, you have a very large latency. Okay, it's got a very low bisection width because you can't do much communication between the two halves of the network. Okay, but it's got a cheap cost, so that's the one advantage that it has. Now you can add one additional link to the linear array, and you can get a ring, right? So here you just connect the first processor with the last processor. Okay, when you do this, you're going to improve your diameter, because now if you have p processors, then the diameter becomes basically p over 2. Okay, you also improve the bisection width because now you need to cut 2 links in order to split the network in half, right? So the bisection width goes from 1 to 2. Okay, and the cost is still small because we just added one more link. So now the cost is p. Now you can go from the one-dimensional array to a two-dimensional array. Okay, so the two-dimensional array is usually called a 2D mesh. Okay, so for the 2D mesh, the diameter improves a lot, right? So if we have p processors in this 2D mesh, okay, so if there are p processors overall, like 16 processors over here, then basically the dimensions of this mesh is going to be square root p by square root p. And so therefore the diameter of this network is what is the farthest pair of nodes in this network? What's basically these nodes at the corners of the network, right? And the distance between them is, well, we have to go all the way up and all the way across, right? So that's basically going to be root p plus root p. So it's something like 2 times root p, right? Minus 2. Okay, so we've gone from this diameter of p in the 1D array to a diameter of 2 times root p in this 2D array. Okay, so much better. And the bisection width is also pretty good for these networks, because if you want to split this network in half, right, then what you need to do is you basically need to cut across the network. Okay, so now how many edges do you need to cut? Well, you need to cut square root p edges, right? You need to cut all of these edges. Okay, so again, compared to the 1D topology, which has a bisection width of 1, right now we have a much higher bisection width, and we can do more communication between the two halves. And the cost hasn't increased too much, right? So the cost is basically, you see that every node, right, or sorry, every processor, basically you can sort of associate 2 links with that processor, right? And some of these processors at the edge, well, you only associate 1 link with those processors. So if you do a bit of math, you can see that the total number of links in this 2D mesh is something like 2 times p minus 2 times root p. Okay, so now you can actually, just like we could go from the linear array to a ring by adding one additional edge between the first node and the very last node. Now for the 2D mesh, we can do that for every row and every column. Okay, so for each of the rows, we're going to take the first node and connect it to the last node. Okay, so that's going to form a ring for this row, right? And we do that for every row. And then you do the same thing for the columns. Okay, so every column is also a ring. And when you do that, you're going to improve the diameter. Okay, so it's so basically now instead of the farthest 2 nodes being these corner nodes, right? So now these corner nodes actually are very close to each other, right? They're connected just by 2 hops. Okay, so now the farthest nodes are the nodes which are basically in the center. Okay, and those from the corner nodes, those need to take root p minus 1 hops. Okay, and also by adding these links from the first to the last node, you also improve the bisection width. Okay, because now if you want to cut the network, right, you see that basically for each of these nodes in a row, right, you need to cut 2 edges. Okay, so you basically double your bisection width. And the cost, there's just a minimal increase in the cost, right? Because you just need to add all of these links on the rows and on the columns. And so that's, you just have 2 times root p number of these links. Okay, so you can go one step farther, right? So you can, so we've gone from 1D linear arrays to 2D meshes, and you can also move to a 3D mesh, right? That's the next natural thing to do. And when you do that, you're going to decrease your diameter again, okay? Because now, if there are p processors in this 3D mesh, then the dimensions of the mesh are going to be, it's going to be root p, it's going to be the cube root of p, right? By the cube root of p, right? By the cube root of p. Okay, so this is also going to be the cube root of p over here. Okay, and now the farthest pair of nodes are again the nodes at the corners, right? But now the distance you need to travel is you need to go all the way across, all the way up, and all the way through this network, right? So that's basically something like 3 times the cube root of p. And also, you also improve the bisection width, because now if you want to cut this network in half, right, what you need to do is basically you need to cut out like a face of this network. Okay, so if you imagine taking that middle face and you cut out like all of the links that cross that face. Okay, you need to cut all of those in order to bisect the network. Okay, well, how many nodes are on that face? Well, this face is going to be root p by root p large. So therefore, the number of nodes on that face is going to be the cube root of p squared. Okay, and then the cost to build this network. Well, basically, you can see that every node here basically has 3 edges, right? It's got an edge in the x direction, in this y direction, and in the z direction, right? Every node has basically 3 edges, except for these corner nodes. Okay, so if you do the math, you're going to see that the cost is basically 3 times p. Okay, so we can even take this this mesh concept farther. So there is this computer built by Fujitsu called the K computer, and what they have is this this network called the TOFU network. So this actually stands for Torus Fusion. Okay, so this is basically a 6D grid. Okay, so the way they get a 6D grid, even though you know, we live in 3D space, is that so they construct this topology hierarchically, where at the high level, right, we have a 3-dimensional grid like this in the XYZ directions. Okay. However, for each of these little nodes over here, right, if you zoom in on that node, then this node over here is in itself a 3D network. Okay, so here we've zoomed, oops. Right, so here, well, let's look on the bottom. Okay, so this is easier to see. So here we've zoomed in on this node. Okay, and you see that this node itself, right? So each one of these little balls over, each one of these little balls, okay? This, when you zoom in, is also another 3 dimensions, okay? Because we have this orange A dimension over here, right? Okay, you've got this this B dimension, which is a torus over here, right? It's a torus because it's you know, it's a ring like this, right? And then you have the the C dimension over here. Okay, so it's basically it's one of these 3-dimensional little structures, right, within another 3-dimensional structure. So altogether, it's going to be a 6D mesh. Okay, more topologies. Okay, so next we have the tree topology. Okay, so here we have a binary tree topology where each node basically is connected to two children nodes, and then you have these leaf nodes which are not connected to any children. Right. So now the great thing about the tree topology is that the diameter is very low. Okay, because if we have P processors over here, right, then what is the height of this tree? Well, because it's a complete binary tree, then the height of the tree, right, the height over here is basically log P, right? If we have P leaves, P nodes in total, then the height is going to be log P. And so therefore the diameter of this network is just, so the farthest pair of nodes, right, the farthest distance they have to travel is all the way up the tree and all the way down the tree. So that's basically 2 times log p. Okay, so it's got a very small diameter, these trees. But the problem is that it has a very low bisection width, right? So it's not possible for, so for example, if you cut the tree like this, right, then there's very little communication bandwidth between this half of the tree and the other half, right? Because all of the messages have to go through the single link. Okay, so to improve on that situation, we have something called a fat tree. Okay, so basically the fat tree is still going to be a tree, but the observation is that as you move up the tree, right? So for example, if we look at the left half of these nodes over here, right? Then you have many nodes over here which want to communicate with many nodes on the right. Okay, and in order to do that, we're not just going to have a single edge over here. We're actually going to have many edges. Okay, so in fact, the way you build this fat tree is that each time you move up the tree, you double the number of edges between a child node and its parent. Okay, so here you have 2 edges. If you move up another layer, you have 4 edges, and then you have 8 edges over here. Okay, so now since you have 8 edges over here and you only have 8 nodes over here, then now each node can have its own dedicated communication edge, right? So basically, the fat tree has a much better bisection width compared to the regular tree. Okay, in fact, the bisection width is going to be p over 2. Okay, the diameter doesn't change because we're still in a tree, right? So the farthest 2 nodes are still the ones at the leaves. Okay, the cost of the tree of this fat tree does increase because as you go up the tree, you need to add more and more edges, right? So basically, each layer of this tree, okay, there are basically p edges at every layer of the tree, right? Yeah, so here you have like what do we have? Like 16 edges, and then on the next layer you have 8 of these squares, right? But then you have 2 edges between them, so that's another 16 edges. Okay, so in total you have log p levels, right? So the height of this tree is log p, right? Oops, log p. Right, so the cost per layer is p. You have p edges per layer. So altogether, you basically have a cost of something like p times log p divided by 2. Okay, I'm almost finished over here. So the last architecture we'll talk about are these hypercube architectures. Okay, so for the hypercubes, so the way that we build these hypercubes is recursively. Okay, so we're going to start with, so we have hypercubes of different dimensions, and we start with 0-dimensional hypercubes. Okay, so the 0-dimensional hypercube is just a single node. So once you have the 0-dimensional hypercube, you can recursively build a 1-dimensional hypercube. So what you do is you take a copy of the 0-dimensional hypercube, which is a single node, and then you make another copy, and then you connect them. Okay, so that's going to be a 1D hypercube. Okay, it's basically a line. Now, once you have a 1D hypercube, you can make a 2D hypercube. Okay, so the way that you can do that is you take 2 copies of these 1D hypercubes. Okay, and then you connect the corresponding nodes. Okay, so now we can also label the nodes in the 2D hypercube. Okay, so the way you label them is that you start from the 1D labeling, right? So the 1D labeling is we label these nodes 0 and 1. Okay, now when you move to 2D, right, we're going to make 2 copies of this 1D hypercube. So for the first copy, we're going to prefix this 0 and the 1 with a 0. Okay, and then for the second copy, we're going to prefix it with a 1 over here. Okay, so this assigns a unique label to every node in the network. Right, it's basically a 2-bit binary number. Okay, so now we want to move to 3D hypercubes, right? So the way we do that is we're basically going to take 2 copies of the 2D hypercube. Now, for the first copy, we're gonna prefix all of these labels by 0, right? So we have 0, 0, 0, 0. Okay, and then for the other copy, we're going to prefix all of the labels with 1. Okay, and then we're going to connect the corresponding edges, right? So we're going to connect the 0, 0, 0 with the 1, 0, 0. Okay, we're going to connect the 0, 0, 1 with the 1, 0, 1, and so on. And so that's going to form a 3D hypercube. And if you continue this process, I'll do one more. So let's draw a 4D hypercube. So we need to take 2 copies of the 3D hypercube. Right? For the first copy, we're going to prefix all of the labels with 0. And for the other copy, we prefix it with 1. And then we connect all of the corresponding nodes. Okay, so you can keep going with this process. So you can form a 5. You keep going with this process, and eventually, if you form a hypercube with p processors, okay, then it turns out that the diameter of this hypercube is going to be log p. Okay, because for example, if you look at the 4D hypercube, right, each time you move up a dimension, right, you double the number of processors. Because in order to form the 4D hypercube, we took 2 copies of the 3D hypercube. Right? So in general, for the k-dimensional hypercube, let me just abbreviate that HC, right? We're going to have 2 to the k nodes in this k-dimensional hypercube. Right? So therefore, if p is your number of nodes, then this 2 to the k is equal to p. And so therefore, the dimension of the hypercube is equal to log of p. And you can see that the dimension of the hypercube is equal to the diameter of the hypercube. Right? So for example, in the 1D hypercube, right, dimension is 1 and the diameter is 1. Right? In the 2D hypercube, the diameter is 2. Right? In the 3D hypercube, the diameter is going from 0, 0, 0 to 1, 1, 1. And so that's going to take you, let's see, it's going to take you 1, 2, 3 steps like that. Right, and in the 4-dimensional hypercube, you need to go, 1, 2, let's see, 3, 4. Okay, to get between these, between the most extreme points. Okay, so the diameter is actually very low, right? Because even if you have p processors, even if you have 1,000,000 processors, the diameter is only log of 1,000,000, which is 20. Okay. Now, the other great thing about the hypercube is that the bisection width is very good, okay? Because if you want to disconnect the processors, right, half the processors, well, then you're going to need to like cut across these edges, right? And how many edges are there? Well, there are 4 processors on top and 4 on the bottom, and you connect the corresponding pairs. So there are 4 edges that you need to cut, right? For the 4D hypercube, right, you need to cut 8 edges. Okay, so in general, when you have p processors, you need to cut p over 2 edges. Okay, so that's a very large bisection width. And finally, the cost of the hypercube. It's not too large because basically each hypercube, if you're in k dimensions, okay, then each node needs to connect, it needs to have 1 edge for each dimension. Okay, so for example, in the 3D hypercube, right, so we have 1 edge in this dimension, right? So this dimension is this the 3rd digit over here. Okay, so we have 1 edge to go in the 3rd digit. We have 1 edge to go in the 2nd digit over here, right? And then we have 1 edge for this final dimension, which is to go from this 0 to this 1. Okay, so in a hypercube, every node is connected to other nodes. Which so if you have a node which has a certain label in the hypercube, right? Then what other nodes is it connected to? It's connected to every other node whose label differs in 1 bit from this node. Okay, so for example, if we have this node, right, then this is connected to every other node which differs in exactly 1 bit from this node, right? So for example, 0, 1, 1 differs in 1 bit, in a single bit. Right? So therefore, we have a connection over here, right? The 0, 0, 0 differs in the 2nd bit, so we have a connection over here. And the 1, 1, 0 differs in the 1st bit, and so we have a connection over here. Okay, so we have 1 connection per digit of each node. Okay, and since we have in a k-dimensional hypercube, we have k digits, right? And we have 2 to the k nodes, right? Then the total cost is going to be k times 2 to the k, right? And so this 2 to the k over here is p, and this k over here is log p, right? So basically the cost is this divided by 2. Okay, so sorry, let me erase this over here. Yeah, so so the hypercubes have very good diameter and also very good fault tolerance and bisection width. Okay, and it's actually possible to construct very high-dimensional hypercubes. So, for example, this Cray CM1 computer, its connection network was actually based on a 20-dimensional hypercube. Right, so this is quite remarkable. Okay, so it's very hard to visualize a 20-dimensional hypercube, but you can actually make some nice pictures for the 4-dimensional or 5-dimensional hypercubes. They look something like this. Okay, all right, so this is all that we're going to talk about in the second lecture. In the next lecture, we'll talk more about communication in shared and distributed memory architectures. Okay, so see you next time.